Okay, thanks for the introduction. Uh, First, I would like to thank my co-authors for uh, making this happen, and also thanks for the audience for this talk. We all know that it's really hard to find an end-to-end application of quantum algorithm, especially for quantum algorithm based on machine HHL algorithm. There's one approach, that is we assume we have a classical nonlinear problem. If we can linearize this nonlinear problem and we map it into a quantum linear system problem, and then this quantum linear system problem will have exponentially large size because of we can apply HHL for quantum linear system problem, we can solve it in polynomial time. And then we will get a quantum solution of the linear system problem. If we have the quantum solution, given the quantum solutions, if we can get the classical program in polynomial time, then we can kind of like get some exponential speed up. It's kind of like a natural killer application of HHL. But the problem is that it's really hard to find such problem. We don't know where to find such problems, in fact. I think recently, in 2017, there is work by Cheng and Gao. They introduced the problem that is solving polynomial systems. You are given a set of polynomial equation, and you linearize this polynomial equation, and by replacing monomials with by linear variables, and you can map it into exponentially large linear system. And this exponentially large linear system can be reformulated as a quantum linear system problem. And then they apply HH algorithm on this quantum linear system problem. And then they, given the quantum solution, they say they prove that you can get a solution of the polynomial equations in polynomial time. And in this example, in this problem, the two mapping steps can be done in polynomial time. But the HHL algorithm depends on the condition number of A, and Cheng and Gao, they did not analyze the condition number. Instead, they pose the questions that there are a lot of problems can be reduced to solving polynomial equations, and they hope some of them might have small condition number. For example, those problems might have 3-side polynomial systems over finite field, shortest vector problem, and closed vector problem. Those problems are known to be NP hard, so we don't expect that we can solve them efficiently. In this work, we are going to analyze the Cheng-Gao's algorithm. We are given a set of polynomial equations with a unique non-zero solution, which is a binary solution. We linearize into a matrix A. The running time of Cheng-Gao's algorithm, as we prove in theorem 1, is that the low bound of the condition number of the A is exponential in the Hamming weight of the solution. This means that the Cheng-Gao's algorithm takes exponential time in the Hamming weight of the solution, at least. This implies, in fact, if we do Grover search can do better. And then we refine the Cheng-Gao's algorithm such that when the Hamming weight is log n, there might be a super polynomial speed up here. Okay, first let's look at the motivation between the solving polynomial systems and the linear algebra. The bad news is that we already know solving polynomial system is NP hard, so we don't expect solving NP hard problem using quantum computer. So the condition number here better be big. The good news is that classically this approach, you map polynomial system to linear algebra, has been used before, has been for some polynomial systems. For example, polynomial system over finite field and bilinear polynomial systems and over-defined system of polynomial equations. And for some of them, it can be done, in polynomial time classically, because it is the specialty of those polynomial systems. And quantumly, the good news is that Cheng and Gao proved that after the linearization step, in fact, because the matrix A and the vector B are both sparse, so we can apply HHL algorithm on this exponentially large quantum linear system problem. Besides that, if we assume each variable is a Boolean value, they prove that you can get a solution in polynomial time. You are given the quantum solution. Again, they did not analyze the condition number. Okay, let's see. The classical and the quantum approach, they are not quite the same. They are a little bit different. Classically, you're given a polynomial equation. You are linearize this polynomial equation. You generate exponentially large number of polynomial equations by multiplying monomials under a certain degree. Then you have a matrix that is called Macaulay matrix, which I will define it later. I will define it later how it looks like. And then after you got the Macaulay matrix, you can do Gauss elimination, and you can look at the rule-reduced Macaulay matrix. You triangulate this Macaulay matrix. You can extract the Grobner basis from this triangulated Macaulay matrix. But this is not possible, for quantum algorithm because we cannot do Gauss elimination using quantum algorithm, and also we can't look at the rule-reduced Macaulay matrix. And instead, we can do something different, but still works. That is, we solve the quantum linear system problem. That is AY equals B. Here, A is the submatrix of the Macaulay matrix with additional column minus B. We will have the Macaulay matrix. Here, B represent some constant vector appear in the polynomial equations. So now the question is that where does the matrix A come from? In Cheng and Gao's paper, they introduce a polynomial system that is called the Boolean polynomial system, which means that for the polynomial equations, which is have quadratic, it is a quadratic polynomial system equation. The degree is at most 2, which guarantee the sparsity of the matrix. And also we have the field equation that is guarantee each variable, F2 here, each variable is a Boolean value. The Boolean value of each variable can guarantee that we can get the solution of the polynomial equation given the quantum solution of the linear system problem. In fact, they prove that they reduce solving Boolean polynomial system to a super exponentially large linear system problem. And this super exponentially large linear system can be easily connected to the HHL algorithm. But the running time, as we mentioned, it's unknown because the condition number is unknown. Let's look at how the matrix, how the linear super exponentially large linear system looks like. For example, suppose we have a polynomial f. It can be represented by a row vector. In fact, if we have the monomial basis, it look like this. For each polynomial, we will have a row vector of a matrix. It can be represented by its coefficient vector. Now, suppose we have f1, then we can fill the coefficient vector of f1 as a row vector into a matrix, and then we have f1 to fm, and then we have m rows, and then we multiply each polynomial to a monomial. And these monomials are under maximum degree approximately D. How many monomials are there? There are, depends on the choice of D, there are might be exponential number of monomials, which means then we can generate exponential number of polynomials, and we put them as the root vector of this matrix. And then we also here we assume the maximum degree of the monomial that involved in the that appeared in all the polynomial equations is at most D. After this step, we replace each monomial as a new linear variable, and then we will get a linear system that is a y equals b. Here b represents the constant terms that appear in the polynomial equations. Noted that for Cheng and Gao, they proved that for higher enough D, we can get a correct solution for this, super exponentially large linear system. And also, we know that because we multiply a monomial, then for any polynomial equation, if we multiply a monomial, then there is no constant term anymore. So the vector B is sparse vector. Also, the matrix A is also Mn squared sparse. So which means that we can apply HHL algorithm to this super exponentially large quantum linear system problem. The problem is that what is the condition number of A? Next, we will provide the low bound of the condition number of A. First, let's assume S is the unique non-zero solution of the polynomial equations, and H is the Hamming weight of the solution S. Then we have the theorem 1. The low bound of the condition number of A is exponential in the Hamming weight of the solution, which is 3n to the h over 2. This means that the low bound is depending on the Hamming weight of the solution. It means for different Hamming weight, we will have a different explanation. Then first, that is Cheng and Gao's algorithm, of course, that takes exponential large with respect to the Hamming weight of the solution. Especially when when the Hamming weight is a constant, there always exists a classical algorithm can solve it efficiently in polynomial time. And when H is larger, then we can, using Grover search and by increasing the Hamming weight to Grover search, we try all the possibilities, then Grover can do faster. Okay, let's see how to prove theorem 1. It's quite simple. We are given, the definition of condition number A, which is the norm of A multiply the pseudo inverse of norm A. The norm of pseudo inverse. And the first inequality is obviously true. It's a fact. And the second inequality holds because here the norm of A it is always greater than 1. And without the loss of generality, we can assume the norm of B equals 1. In this case, we have the low bound of the condition number of A is the norm of the solution vector, which is S hat. How does this S hat, the solution of the super exponentially large linear system, looks like? We know the vector is also super exponentially large, which is 3n to n, and because the solution is a binary solution vector, so it has either 0 or 1. In fact, how many zeros, how many ones are in its solution vector? It is d plus 1 to the h minus 1. Here, d is the maximum degree we defined previously. And in Cheng and Gao's paper, they use d equals 3n. In this way, we can prove that the low bound of the condition number of A is 3n to h over 2. And the Grover can do fast. So it seems that this attempt does not work. And the problem is that we know HHL algorithm is a BQP complete. We expect the HHL algorithm to be powerful. So we're trying to see whether we can do better. The answer to this question is yes, we can do better. In fact, we will show that we can refine the algorithm. We can refine Cheng and Gao's algorithm, and our refined algorithm takes time at least 2 to the h over 2. In this case, when h equals log n, approximately log n, then it's potentially there might be a quantum polynomial time algorithm for some special polynomial systems. In this case, the classical brute force, if when h equals log n, it might be super polynomial large. Okay, how can we do better? We know we can do better, but how can we do better? Remember that we said that for each variable, they are Boolean values, which means that all the monomials, they have the same value as their square-free version. So we can replace all the monomials appear by square-free version. Based on this observation, we can reduce polynomial system solving to a better, Boolean. We call it a Boolean Macaulay linear system. This Boolean Macaulay linear system has a smaller size. And we solve the Boolean Macaulay linear system AX equals B using HHL algorithm. And the low bound of the condition number of A now is 2 to the h over 2. Besides that, we provide an alternative approach to get the solution of polynomial equations. Let's see how can we reduce a polynomial system to Boolean Macaulay linear system. Here, we extend the definition of Boolean Macaulay matrix, which is defined over F2 before. It had been well studied in cryptanalysis. Here we defined it over to complex field. And for Boolean Macaulay matrix, we have the A and minus B it is composed as the Macaulay matrix. Then we can reduce solving the polynomial equations to a smaller Boolean Macaulay linear system problem. The problem is that the Boolean Macaulay linear system has much smaller size, but can we, still get the correct solution from the Boolean Macaulay linear system? For example, is the Boolean Macaulay linear system, the matrix A and vector B is still sparse? Can we apply HHL algorithm? The answer to this question is yes. The reason the correctness of this Boolean Macaulay linear system is solving this Boolean Macaulay linear system is equivalent to solving the Macaulay linear system. Remember that the Macaulay linear system is very large. It's much bigger large. We have the non-square free monomials. We also have the square free monomials. And if we replace all the non-square free monomials by a square free monomials version, then we can get it corresponding to some root operation on the Macaulay matrix. After certain root operation, we have the Macaulay matrix in this form. And the Boolean Macaulay matrix is a submatrix of this row-reduced Macaulay matrix. In this way, if we can solve the Boolean Macaulay matrix, Boolean Macaulay linear system, we can instantly get the solution of the Macaulay linear system, or vice inverse. So in this way, we can we show the correctness of our Boolean Macaulay linear system. We can get the correct solution from this linear system. How about the HHL? We want to solve this linear system, Boolean Macaulay linear system, using HHL algorithm. Are the two mapping steps still efficient? The answer is also yes. The matrix A is sparse, still sparse. And vector B is also sparse. It can be efficiently prepared as a quantum state. Besides that, we can get the solution of the polynomial equations in polynomial time. Besides that, we also have the rank of the matrix A is exponentially large, which means that it cannot be dequantized by classical algorithm. How about the condition number? Let's look at for the Boolean Macaulay linear system, how the solution looks like. Still, we have the unique non-zero solution of polynomial equations. Then in this case, for the Boolean case, we only consider square-free monomials. So the number of ones in the solution is 2 to h minus 1. So by theorem 1, we have the low bound of this condition number is 2 to h over 2. And the low bound of the condition number A, in fact, is a polynomial. So there is an open question. That is, are there any polynomial systems with the corresponding condition number and also upper bounded by a polynomial? In this, if so, we can have a kind of like a super polynomial speed up here. Here's the open question. Now we have analyzed our performance of the refined algorithm. I still have one part I did not cover. That is how to get the solution from the how to get a solution of the polynomial equations from the quantum solution. First, let's look at how the quantum solution of the Boolean Macaulay linear system looks like. We know that it is a binary solution. It is either 0 or 1 in the solution vector. Suppose we have, not suppose, we have n variables, x1 to xn, and we have an unknown subset that all S, which has all the variables in this set has value 1. Then the quantum state will exactly looks like a superposition over over all the subsets of S. It's kind of like a uniform superposition on the support of the solution vector as high. In this way, if we measure some variable, for example x1, with probability almost 1/2, we can collect this solution. The question is, we want to collect all the solutions in all the variables in the set S. Given copies of this quantum state, how to compute this S? The answer to this question is we have the quantum coupon collector problem. In fact, here is the variant version. We have an unknown subset we want to compute. We're given copies of the state, which is a superposition of subset of S of size at most d. And we have a theorem. That is, if we can imagine R copies of quantum superposition states, the quantum solution of the Boolean Macaulay linear system, then with high probability, you can correct the solution. The good thing is that when D equals the cardinality of S, which is the Hamming weight of the solution, then we only need a logarithmic of the Hamming weight of the solution to get to collect all the solutions. Especially when D equals 1, it is corresponding to the quantum coupon collector problem, which is defined in this paper. Okay, here I give the summary. We show Cheng and Gao's algorithm is exponential in the Hamming weight of the solution. And we refine this algorithm to open the possibility of quantum speedup when the polynomial system has Hamming weight h equals log n. And for problems like polynomial system over finite field and so on, and also factoring, the Hamming weight of the solution is going to be increased, it's going to be increased dramatically when reducing to polynomial equations. So we cannot gain much speed up here. Also, our analysis also applies to the truncated HHL algorithm, which is only inverted on the well-conditioned subspace. Besides that, we give an alternative approach to extract the classical solution where the generation of the quantum coupon collector problem. Here are some open problems. That is, first is find some special polynomial system to exhibit the potential super polynomial speed up when h equals log n. The second one is that in this paper we only consider the unique solution case, or we only consider the unique solution case. That is, the polynomial equation has a unique binary solution. How about the multiple solution case? Our refined Boolean Macaulay linear system also works for the multiple solution case. And this might open more possibilities of quantum speedup when considering multiple solution case. The last one is proving the matching low bound of the variant of the quantum coupon collector problem. Here is all the open problems, and this is my talk. Thank you for your listening. Any questions?
Oh, okay, thanks for the nice talk. I will maybe just again post a question here which was asked in the Slack channel by Ronald DeWolf. A lower bound on the upper bound in terms of kappa of the algorithm's runtime does not imply a lower bound on the runtime of the algorithm itself. So this is actually an ongoing discussion on the Slack channel. So I guess it refers to whether, yeah, how the so to say the condition number cup is related to the actual runtime, and also for which, I mean, yeah, for how does it look like for these concrete polynomial systems?
The low bound of the condition number is the low bound of the HHL algorithm. The time complexity of the HHL algorithm, because the algorithm apply HHL algorithm, so the low bound of the condition number of A is also a low bound of Cheng and Gao's algorithm, also our algorithm. It's only a low bound. Is that what he wants to ask?
I guess so, but I mean, I guess we can just follow up on the. I mean, it's an ongoing question.
Yeah, I feel confused when you say, you know, a low bound of upper bound. Yeah, I'm not sure I understand it correctly. Okay.
Yeah, I guess it's just, you know, when you when you only have a lower bound on some upper bound, it doesn't really bound the quantity itself, right, necessarily. Okay, but otherwise, I mean, I just want to refer everyone to the roundtable, which will actually start now in 1 minute, basically, for one-to-one discussions and asking questions with the speakers of this session, right?
Okay.
Yeah, with that, since we are actually at the end of the time slot, I would